We're going to jump back into the second half of Engage New York Lesson 11, where we focused on completing the square. You might remember Wednesday rewriting some quadratic expressions in standard form, that's ax squared plus bx plus c, in the equivalent completed square standard form. Let's start with an example, r squared plus 4r plus 3. We know how to factor this expression from way back when. The first term in both of our binomials will be r because we're multiplying r times r to get r squared. And we'll need a number that multiplies with another number to get 3. And the sum of these two numbers will be 4 because we have a b term of 4 and a c term of 3. We'll end up with 3 and 1 because 3 times 1 is 3 and 3 plus 1 is 4. This should be pretty simple for you guys, and if you wanted to check my work by factoring it out, you would get right back to a standard form of r squared plus 4r plus 3. Now, the second way that we could rewrite this expression is by completing the square. And hopefully you recall from Wednesday that when we start completing the square, we want to focus on our a term and our b term. We know that the first thing in both parentheses will be an r value by itself. And whatever term comes after r will need to add to 4r. Because, of course, when we multiply these two numbers, we'll get the third term, but we know that we need to add them together to get the second term. So we'll have positive 2. When we factor this expression, we end up with r squared plus 2r plus 2r plus 4, because we're multiplying that 2 times 2. And we can simplify this to r squared plus 4r plus 4. Now, we did not end up with an expression that is equivalent to r squared plus 4r plus 3 because our constant term is a 4. And again, here it's a 3. However, we can easily manipulate, that means change around, our expression in order to make it equivalent. So we need this term to be a 3, and we can easily change a 4 to a 3 by subtracting a 1. However, remember that anytime we mess with an equation by adding or subtracting, we need to make sure we do the opposite so that it's really no change at all. So I'm going to add a 1. So now I've taken away a 1, I've added a 1, and if I rewrite my expression, I have plus 3 plus 1 because I subtracted 4 minus 1 and I added 1. Now, of course, we know from the first step of completing the square that r squared plus 4r plus 3 is the same thing as r plus 2 times r plus 2. So I can simply change the first 3 terms of this expression to r plus 2 squared plus 1. Both of these expressions, r plus 2 squared plus 1 and r plus 3 times r plus 1, are equivalent to my original expression, r squared plus 4r plus 3. Even though we didn't end up with a perfect square in this expression, it was still pretty simple to change our plus 3 to plus 3 minus 1 plus 1. This example is a little bit trickier. We've got y squared minus 3y plus 10, and we're going to focus on completing the square. So if I have y squared minus 3y, I know that the first term in my binomial will be a y, And I need to think about what numbers add up to negative 3. Now, obviously, negative 3 is an odd number, which means when we split negative 3 in half, we're going to end up with a decimal or a fraction, however you want to write it. In this case, that fraction can be represented as 3 over 2. And the reason why that's the case is because negative 3 halves plus negative 3 halves equals negative 3y. And I can prove it because if I factor my expression, I end up with y times y is y squared minus 3 over 2y. That's 3 over 2 times y. And then the second negative 3 over 2 times y. And then I'll actually have negative 3 over 2 times negative 3 over 2. So I'm multiplying top times top and bottom times bottom to get positive 9 over 4. Now, before we even deal with this constant term, let's recognize that this expression is equivalent to y squared minus 3y plus 9 over 4, because 3 over 2 is really just 1.5, and a negative 1.5 plus another negative 1.5 gets us a negative 3. Okay, so we're good on our A term and our B term. They match our original expression here, but 9 over 4 obviously isn't the same thing as 10, which proves that this expression is not a perfect square. And when I say not a perfect square, what I mean is we're going to have to do some messing around with this constant term to make sure that we can create an expression that's equivalent to y squared minus 3y plus 10. So we know that our constant term is 10, but we're working with fourths. So I'm going to go ahead and quickly take my whole number 10 and convert it into fourths. And I'm just going to do that by multiplying times 4 over 4, which is, of course, the same thing as 1, making 10 equivalent to 40 over 4. What this means is that I can rewrite my original expression as so: y squared minus 3y plus 40 over 4. This expression here is exactly the same thing as our original quadratic expression. I've simply changed 10, the integer, to the improper fraction 40 over 4. Now, I want to end up with y squared minus 3y plus 9 over 4 in my expression so that I can convert at least part of my expression to a perfect square. Notice that I can easily split up 40 over 4 into 9 over 4 plus 31 over 4. I knew that I wanted to convert 40 over 4 into these two improper fractions added together because I wanted a 9 over 4 constant in my expression so that I could convert my first three terms into that perfect square, y minus 3 over 2 squared. And if you're a little confused about where I got that from, remember back when we took y minus 3 over 2 times y minus 3 over 2, which is of course the same thing as y minus 3 over 2 squared. And we factored out our expression to demonstrate that it was equivalent to y squared minus 3y plus 9 over 4. Now, of course, I can't forget that I have this 31 over 4 still as a part of my expression, because remember, we needed to set this entire expression equivalent to y squared minus 3y plus 10. So I'm going to go ahead and add that to my final answer. And I end up with my perfect square, y minus 3 over 2 squared plus that 31 over 4. Not the best box, but you get the point. I'm going to start one more example, and you guys are actually going to have a chance to finish it in your work for today. We've got k squared plus 7k plus 6. So again, we're going to start by focusing in on those first two terms, k squared plus 7k. And we know that if we were to create a perfect square with those two terms, we would need 1k in both binomials, and our second term would need to add to 7. Now again, 7 is an even number, but if you think about half of 7, you could write it as either 7 over 2 or 3.5, because of course 3.5 plus 3.5 is 7. I'll prove that this binomial, k plus 7 over 2, gets me back to my a term and my b term that I have in my original expression. By factoring, I end up with k squared plus 7 over 2k plus another 7 over 2k plus 7 over 2 times 7 over 2. And when I'm multiplying those two improper fractions, I'll do top times top, bottom times bottom for 49 over 4. And of course, I can combine my like terms to simplify for k squared plus 7k plus 49 over 4. Now, again, our constant term does not match our original expression, so we're going to need to play around with that improper fraction so that we can include the perfect square in our final answer. Just like our last problem, I'm going to want to convert my integer 6 to an improper fraction over 4 so that we're working with the same denominator. We'll end up with 6 times 4 equals 24 over 4. So I can rewrite my original expression as k squared plus 7k plus 24 over 4. Now, to include 49 over 4 in my expression somehow, I'm going to need to add to my constant. In the problem before, we were able to split up our constant to include our desired constant term for our perfect square. However, in this case, 24 over 4 is less than 49 over 4. So I know that to get 49 over 4, I'm going to need to add 25 over 4. But remember that anytime I add to my expression, I want to be sure I'm not changing its value, so I'll subtract the same amount. And then I can simplify by focusing on the first 4 terms, k squared plus 7k plus 49 over 4. And I can't forget about this minus 25 over 4 because, of course, I got 49 over 4 by combining the like terms 24 over 4 plus 25 over 4. But I don't want to subtract this 25 over 4 because I would end up just where I started with 24 over 4. And I need this 49 over 4 as a constant so that I can use my perfect square. We'll pause there. I'm going to ask you guys to finish this problem as one of your questions for classwork today. If you are feeling confused about how to complete the square at this point, I strongly recommend you reach out to me, give me a call, schedule some video time so we can go over it before you complete the assignment, because I want to make sure we're all on the same page before we move on. Otherwise, I hope you have a great week and happy Monday.